At the end of the lesson, you are expected to define the features of principal component analysis, follow the process of doing principal component analysis, and appreciate the significance of principal component analysis. In this session, we will study more about the weight of the variables in our data. So if you could still remember our past lessons when we talked about decompositions and we factored our matrices or our data. So this lesson is actually a notch higher than our previous one. So the link of lesson number 11 is given in the description below, and I suggest that you study and watch lesson number 11 for us or for you to be able to understand this lesson very properly. You may pause this video for a while and then come back if you're done with lesson number 11, 10, and even until 1. So the major question for this lesson, or the questions for this lesson, are: what is a principal component analysis? What kind of method is the principal component analysis? So we will have these questions one by one. And to start with, principal component analysis is actually a data analysis that is usually used to reduce the dimensionality. So when we say dimensionality, it is about the number of variables of a large number of interrelated variables. So, but at the same time, it retains as much of information as possible. So noting this fact, that it reduces the dimensionality or number of variables, it affects accuracy, of course, because when we reduce something, it affects the information that the real amount of data contains. So, however, this effect in the dimensionality and the information it contains is not substantial, as it only compromises a little accuracy for the sake of simplicity. So the reason for simplification is that it makes it easier to explore and visualize and analyze the data. So the effect is that it makes our algorithm work faster. So let's have the necessary steps, because you would ask me, how are we going to do the principal component analysis? So for better understanding, we're going to go to the step-by-step process of the principal component analysis. So there are actually 5 steps that we have to take note of. So the first step is what we call standardization. So what do we do in standardization? The main goal of this step is to standardize the range of the initial variables. So this is to see to it that each one of the variables equally shares to the analytical process. So for example, we have this situation. So our first variable has a range between 0 to 50. Let me repeat that. The first variable, let's name this variable A. This is an A variable. It has a range between 0 to 50. And then we have the second variable, let's call it B. So the B variable has a range between 0 and 10. So can you see the disparity of the ranges? So if this kind of ranges are to be followed, then the first variable A in this case, will dominate the second variable and make the result so biased. See? So remember, it's 1 to 50 and 0 to 10. Obviously, because the range is so big, then it will just dominate 0 to 10 or variable B. So it's as if variable B has no effect at all. So in this case, standardization, being sensitive to variances, works to avoid this kind of problem. So what we do here is that we get the z-scores of each value. So to get a z-score, we use the following formula, or this formula. We have the z is equal to the value, the each value in every variable, minus the mean for each variable, the mean of the variable considered, and then divided by the standard deviation. Okay, so we will have as many mu or mean as we have the number of the variables. So when we have variable or variables x, then we also have the y variable and then the z variable. So we're going to get the mean for each one. Okay, and then we will do the computation for each value of each variable, and then that's how we get the standardization. So the next thing to do is that after we are done with number one, what we're going to do is that we're going to compute for the covariance matrix. So what is this covariance matrix? So like the first step, it also has its main goal. So this step helps us understand the variables of the input data vary from the mean with respect to each other. So in other words, it describes the relationship between them. So it tells us the presence or the absence of relationship. So for better understanding of what I have said, let us have this example. So this is a three-dimensional data set because it contains three variables. So we have the variable x, we have the variable y, and then we have the variable z. So how to do this is that we're going to relate x to itself, y to x, then z to x, and vice versa for all of them. So this kind of matrix is also what we call a covariance matrix. So what does this covariance matrix mean? So here we have as many entries as, or we have as many entries of covariance as there are pairs of variables. So I want to point out that this pairing is based on the initial variables. So again, our initial variables are x, y, and z, and then in this case we have three variables again. Then we have three combinations for each one. So for x we have three combinations, for y we have three combinations, and then for variable z we have three combinations. And if you're going to total them, all in all we do have 9 combinations. So each combination has its own covariance. So what you can see in the diagonal is the covariance of each initial variable with itself. So where are they? So we have x with itself, then we have y with itself, and then we have, okay, z, x, y, z. So I got a mistake. Okay, that is z. Okay, then we have the z with itself. So again, this is the diagonal covariances, and what you could see again here is the covariance of the variable with itself. So this kind of covariance matrix is actually what we call symmetric. Okay, so what is the meaning of the covariance? Maybe you would like to ask me, because this kind of concept is very important to go further. So if the covariance is positive covariance, then the two variables are correlated. So they may increase or they may decrease together. So if it is negative, it means that the two variables are inversely correlated. So it means that when the other increases, the other variable decreases, or when the other variable decreases, the other one increases. So they are not correlated. So after doing this, we are ready for the next step. So what would be our next step? The next thing to do is to compute for the eigenvectors and eigenvalues. So we have our step number 3. These eigenvectors and eigenvalues are the eigenvectors and eigenvalues of the covariance matrix to know the principal components. Okay? So for each one, we're going to get the covariance matrix. So when we say principal components, they are the new variables that are constructed as linear combinations of the initial variables. So let's go back first. Right, remember we have x, y, z. These are our initial variables. Then we make combinations. So now they become the principal components. Okay, the principal component, which should be a linear combinations of the initial variables. So basically, what we do here is we compress. Okay, we compress the information we found in the initial variables into the first components. So for example, if we have 5-dimensional data set, we have 5 principal components or 5 principal variables. So what PSA does is it tries to store the maximum information in the first component, then the remaining maximum in the second component, until it looks like this. Okay, so as you could see, our bar graph is decreasing. Again, the reason for that is that we are actually compressing the information in the first component, and then the remaining component, the remaining information is compressed in number 2, and what remains is then again compressed in number 3, and then it's compressed in number 4, and then it is compressed in number 5, and so on and so forth, depending on how many components you have in your data. So maybe you would want to ask this time, what's the effect of organizing information this way? So the answer is that this kind of organization allows us to reduce dimensionality without losing much information. So we disregard the components with low information, and how are we going to get or identify if a certain dimensionality has low information? So in this case, for example, how will we know that this one has a low information? So in this case, our knowledge of eigenvalues and eigenvectors is very important. So it is done like this. So in this case, it is the eigenvectors and the eigenvalues that does the magic for us. I think I need to write that. Eigenvectors, because they do the magic. Eigenvectors and eigenvalues. Okay, so they are very important in identifying whether or not a certain dimensionality or component has high or low information. So what we do here is that we rank the eigenvectors or the value of eigenvectors and eigenvalues from highest to the lowest to know the order of significance. So to understand that, let's have this example. So we have here a 2-dimensional data set with 2 variables. So we have 2 eigenvectors and 2 eigenvalues. So for V1, we have these eigenvectors 0.54782 and 0.74215, and its eigenvalue is 1.23462. For the V2, we have 7.48921 and 0.66734, and its corresponding eigenvalue is 0.04824. So based on this, we can say that eigenvalue 1, this one, is higher or is greater than eigenvalue number 2. So let me write that. is larger or is greater than eigenvalue number 2. So what does it mean? So this means that the eigenvector that corresponds to the first principal component is V1, and for the second component is V2. So based on the percentages of the covariances, we can say that the principal component number 1 is 96%, and the principal component number 2 is 4%. So what do I mean by this? It means that the PC1, or the principal component number 1, or the variable number 1, contains 96% of the information of the whole data, and PC2, or principal component number 2, contains only 4% of the information of the whole data. So what will we do next? We have already identified how much information is contained in each principal component. So the next thing to do is to decide whether to keep the components or not. So basically, those that have lower significance or lower eigenvalues may be rejected. So those that remain become a matrix of vectors or feature vector. So in our example, we can actually retain V1 and V2, and then we make a matrix of matrix of vectors, which is called the feature vector, which contains all the components that we retain, or we can reject those vectors that contain lower information. So we could just retain V1 and reject V2. So what will we do then? So bear in mind that the retention of a certain component is actually depending on our own decision. So this is the case where human intuition is very important. So going back, if we reject V2, this will make our dimensionality reduced to only 1. Why? Because we only have one column, we only have one dimension, we only have one variable considered because we reject V number 1. So this result is a loss of information by 4%. So the question now is that, is 4% substantial? Does this really affect whatever result we will have if we're going to reject totally 4%? I think it does not. Why? Because 4% that we've said here is not actually substantial in comparison to 96%. So we can just reject 4%. Okay? So after deciding on what to retain, what dimensionality to reject, what will we do next? So let's go to this step. So in this case, we recast the data along the principal component axis. So in this step, what we do here is we use the feature vector, this vector, or this vector, depending on our choice, to reorient the axis of the original data. So it's something like, for example, let me draw. Okay. Just for example. Okay. Okay. So these are the points of our original data. And then we would like to reorient the axis of our original data. So what we will do is that we're going to use this one. Okay, the feature vector. So this is done by multiplying the transpose of the original dataset by the transpose of the feature vector. So the result would be like this. So originally, for example, we have this data, but then after doing this step, we would have something like this. Okay, so that means the points from here, it goes here. Okay, so they align. What is this for? Why do we have to study this? Principal component analysis is used for dimensionality reduction in order to reduce the number of variables for simplicity. It is also used for visualization, and it is used to filter noisy datasets like image compression. After all being said and done, let's try this. What is a principal component analysis? How do we do the principal component analysis? And why do we use the principal component analysis? Please write your answers in the comment down below. Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. See you in the next lesson.